So this workshop will be focused on HPC clusters such as Mana for using for deep learning tasks. Hoping attendees will also learn about Jupyter Lab and using Open on Demand on Mana and benefits of using GPUs over CPUs for deep learning applications to staging data to direct file systems on for performance purposes when you're doing deep learning jobs. So I'm one of your instructors today. I'm David Schanzenbach. My title, I guess, is Lead Software Architect for Cyber Infrastructure. I mainly help manage the HPC Mana and also everything in between. My two co-presenters are Aditi. Do you want to introduce yourself?
Hi everyone, I'm Aditi as well. I am a graduate student and also Hawaii Data Science Institute fellow, and I am working with Dr. Sadowski, and my main research interest lies in machine learning.
My other presenter is Sorapong.
Hey everyone, I'm also a Data Science Institute fellow. I'm a computer science master student. My focus right now is more of general, applied machine learning and whatnot.
Thank you. All right, so first thing we're going to have you do is go to the setup on the slide or this workshop. There is a file that we require to download. So we will be using Jupyter Lab or Jupyter Notebooks during this presentation and workshop. And there's content that we need you to have. So can you go ahead and download this locally to your own machine? And later on, we'll actually upload it when we need to actually use it. So you would right-click this link and save it to your local machine for now. Other notes are during the presentation, if you have your courage to write comments, questions in chat, and also use nonverbal feedback cues within Zoom to give us feedback about if you need us to slow down, if you have a question, things like that. If you don't know what the nonverbal ones are, there's reactions, a link within Zoom that you can use that has, hand raised if you want to have us, if you want to speak up, we're going to mute you in that case, and check boxes say you're good or, red X and you have problems, things like that. Okay, so let's start with the actual presentation now. So what is HPC and what is HPC or high performance computing? So what is it? What is an HPC system? So the word cloud and phrase cluster or high performance computing or HPC are used in a lot of different contexts and with various related meanings. So what do they mean? And more importantly, how do we use them in our work? The cloud is a generic term, typically commonly used to refer to computing resources that are provisioned to users on demand or as needed, or represent a real or virtual resource that may be located anywhere on Earth, basically. So, for example, a large company could have resources in Brazil and Japan. Let me manage those resources as their own internal cloud for the same company. You can also have commercial clouds such as Amazon's cloud and Google's cloud resources. Let's see. And basically, these are sometimes served for websites, providing shared storage, providing web services such as email or social media platforms, as well as other more traditional computing intensive tasks such as running simulations. The term HPC system, on the other hand, describes a standalone resource for computational intensive workloads. They typically comprise of a multitude of integrated processing or storage elements designed to handle high volumes of data and or large numbers of floating point operations with highest possible performance. For example, all the machines on the top 500 list are HPC systems. If you don't know what the top 500 list is, it's a list of basically the top 500 systems that are speed-wise systems in the world, basically. So I guess that's supercomputing and international supercomputing, which are two conferences in the HPC field. They basically have people run tests on these large machines, and they basically duke it out for who's going to be top in the world. To support these constraints, an HPC resource must exist in a specific location. It has to be a fixed location. So mainly because you have things like network cables can only go so far, optical signals can only travel so far, and you have limits, physical limits of speed of light. Since the longer they have to travel, the longer latency, the slower your jobs might be. So performance is impacted based on distance. So what else are HPC systems good for? Well, typically you use them for large problems. HPC clusters can also be used for even smaller cases where single servers are all you need. Or you have research problems that require tasks are very short, but you have thousands of them. This is more known as high-throughput computing. So what makes up an HPC system? So individual computers that comprise a cluster are typically called nodes, although you will also hear them referred to as servers, computers, or machines. On a cluster, there are different types of nodes with specialized tasks. So what actually makes up a node? So all nodes on an HPC system have the same components as your laptop or desktop would have. They have a CPU, sometimes also called processors or cores. They have memory or RAM, and disk space. CPUs are a computer's tool to actually running programs and calculations. Information about current tasks is stored in the computer's memory, and this refers to all storage can be accessed like a file system. This generally storage can hold data permanently, such data is still there even after the jobs or a compute node or computers restart it. So it's permanent storage, basically, in a sense. While the storage can be local, such as a hard drive inside the machine, it's more common on clusters that nodes have a shared storage that's usually remote or network file shared across the cluster itself. Other specialized nodes in a cluster include login nodes, which serve as access points to the cluster. As a gateway, it's suitable for uploading and downloading small files. They're specialized data transfer nodes. So if you want to transfer large amounts of data from or to the cluster, some systems offers dedicated nodes for this purpose. The motivation for this is large data transfers can obstruct login nodes, so you want to try and prevent that from happening, since if the experience on login nodes is poor, users have a bad experience and causes problems. Rule of thumb, consider large transfers to be maybe something over gigabyte in size, but these numbers can change depending on the particular network and setup that you're working with on each cluster. Our cluster at Mono itself actually has 2 data transfer nodes available for people to use. Compute nodes. So this is where the real work on the cluster gets done. These are the worker nodes, basically. So compute nodes come in many shapes and sizes, but they're generally dedicated to long and hard tasks. They require a lot of computation resources. Different types of nodes you would find include things that have GPUs in them, so specialized processors, large memory nodes, which have upwards of 1 terabyte of RAM in them for large data sets that need to be all in memory, and standard compute nodes, which are mostly just CPU-based machines. All this interaction with these compute nodes on a cluster are handled by a scheduler. In the case of Mono, we use a scheduler called Slurm, or the Slurm Workload Manager. The final type of nodes seen on clusters is the support nodes. These specialized machines basically manage the disk storage, user authentication, and other infrastructure-related tasks, but typically you don't log into these as users. They enable a number of key features to ensure, like your user account files are available throughout this HPC. So, in a nutshell, that's what an HPC is. So, how would you connect to one of these things? So, how do you connect to a remote HPC system? So, connecting to a remote HPC system, the first step is using a cluster to establish a connection from your laptop or desktop to the cluster. When we're seeing a computer or standing, holding, could be your watch, could be whatever, we've come to expect a visual display of icons, widgets, and perhaps some type of windows or applications. So graphical interface of Gui. Since HPC systems are remote resources that connect over long, possibly slow or laggy interfaces, typically stuff like Wi-Fi mixed in with virtual private networks or VPNs, it's more practical to use command line interfaces or the CLI, in which commands and results are transmitted as text only. Anything other than text, such as images, would require to be written to disk and open in a specialized program. If you ever opened a Windows command prompt or Mac OS terminal, you have seen the CLI or command line. If you've already taken one of the carpentry courses on Unix Shell or Vertical, or even the one we did last week, Scientific Software Basics, you would have also seen the CLI or used it as well. The only leap to be made here, though, is opening a CLI on a remote machine. While taking some precautions so that the folks on the network can't see what you're doing, basically, so you don't, and they can't modify the results of whatever data you're sending to the machine or what's coming back to you. These days, we use what's known as secure shell or SSH to open an encrypted network connection between two machines to allow you to send and receive text data without worrying about prying eyes. So as pictured here, you have a laptop and it goes to the internet and connects to a cluster and back and forth. So data is transferred through the internet to your local machine, to the cluster and back. So traditionally, to connect to HPC systems, you use secure shell itself. So most modern computers these days have a built-in SSH client. So if you're running Mac OS, Windows, or some Linux distribution, you have a SSH client built into your system. There's also add-ons now these days for web browsers to have SSH built into them. So Chrome has plugins that have SSH built into the browser for you. But they all operate in a similar manner. SSH clients are usually command line tools, which provide where you provide basically the remote machine address as only required argument. If your username on the remote machine doesn't match your local machine, you also have to provide that as well. There are some graphical tools that are typically seen under Windows, such as PuTTY or MobXterm, which you basically provide some of these arguments after you hit connect. Typical way you see this seen on the command line is for the SSH, you have you type SSH, a space, the username you want at whatever machine or host name. So for example, if we're trying to connect to Mono using SSH, you type SSH, the username in this case is DAV at mono.ids.edu. Do take note, if you do use an SSH client on the command line, typically when you start typing your password, you will not see anything printed. This is a security feature, but it is being printed. So once you hit enter or typed into the system, so once you hit enter, it'll return to what it looks like normally, where it'll see another prompt. If it succeeds, it'll tell you that. If it doesn't, it'll ask you again for the password. Alternatively, there's a thing called open on demand, which is an alternative to SSH in our case. So while SSH is a common method to connect to HPC systems or servers, tools such as open on demand basically provide same functionality or more. Open Demand is actually a software product that came out of Ohio Supercomputing Center based on 2 different grants. If you want to read more or learn more about it, we provide a link here to the site for Open on Demand. Features of Open on Demand could include things, so it basically is used in a web browser, making it possible to connect to your HPC system from any device. So you can even connect from your phone if you really wanted to. Is built-in functionality for file browsing, uploading and downloading files of typically smaller sizes, text editing, SSH terminal, and even submitting interactive applications such as remote desktops to compute nodes, Jupyter Lab, or RStudio. Interactive applications are other institutions. So on Mono, we only have a small subset of applications available as interactive apps, but there's actually a long list of other what institutions have come up with that can be used. So that's a public list that basically, if something seems interesting and it's useful in your research, it is something that we could potentially consider installing on Mono to better your workflows. Browser choice. So if you're to log in, which we'll do shortly, you'll see something like this once you first get to Open on Demand page for Mono. A few things to note about Open on Demand is they do have some preferences towards browser choice and security preferences that you may want to follow. So Open on Demand, developers typically recommend Google Chrome as your browser choice, mainly because it has the widest support for the tools that are used to create Open on Demand. But they typically support any modern web browser. They do explicitly call out that they do not support Internet Explorer 11. So it has to be something modern, but it can't be, it has to be somewhat modern. For security purposes, they do recommend using incognito or a private browsing mode when using Open on Demand. This basically simplifies your logout process where you just close the window out to actually relinquish your credentials. There's potential that the logout function may not work as you intend, that's why. So the story we typically give is, let's say you're trying to use Open on Demand for Mono on a public terminal. you log in and then you walk, you think you log out and you close the browser. Someone else will come along, potentially get into the history of that browser, and you still log into the cluster. So therefore, they would have access to your account on our machine. Versus with an incognito browser or window, once you close out that window, your credentials are wiped so that they can't do that. So at this point, we would like you all to basically try and log into Mana. So we'd like you to open a web browser, start a private browsing window, and then try and connect to this link, https://mana.its.edu. And once you have all done this, please do give us feedback in chat or in, as I said, virtual feedback through the reactions as well. So let me know that you have either problems or if you've got successfully been able to log in. So is Mana part of the White House Institute? So Mana itself is, in the sense that cyber infrastructure is also tightly integrated with White House Institute. Sean, maybe you can speak a little more to this specifically to that question, if you're there.
So I guess it's not just a resource that's for the Hawaii Data Science Institute. It is a system-wide resource that is for all the institutions within the University of Hawaii system. So we do collaborate a lot with the Hawaii Data Science Institute, and as David said, the ITS cyber infrastructure folks that support this, and ITS that houses this resource does work a lot with Hawaii Data Science Institute.
And this is Ron Merrill here. I'll also add that, of course, the name Mana was basically Jason Lee's choice, and the change from it being called UHPC to Mana coincided with a major research instrumentation grant from a National Science Foundation that upgraded Mana. So all of the modern part of it that's community is from that grant. And of course, Jason is one of the co-directors along with Gwen.
So I think I've seen about eight people so far say they've successfully gotten in. Anyone that hasn't responded yet have any problems or encountering something that doesn't seem right and not seeing something like this once you've logged in? Okay. I will, it seems a good chunk of you, or many of you have already gotten in, so I'll continue forward. So when you once you've logged in, you would see something like this, as we said. Yeah, more inspirational, yes, I know, Peter, but but yes, it is what it is right now. So it needs to change. It's sort of a stat thing on the site, but basically it's sort of what's on the command line right now when you enter SSH. But yes, we can always change it to make it more inspirational. Maybe we need some inspirational words that we can place up there for when people log in. But let me see here now. Get my slides up here. So walking through the site just briefly, the first thing that you look at is the top here, basically. So there's a files, there's jobs, clusters, interactive apps. Files allows you to basically open up your home space on the cluster or on Mana to basically see a graphical view of it. So much as if you're on your local machine where you can sort of browse the file system, it has a file browser built in. So this is where you can do things like add new files, add new directories, upload or download small files, delete files, etc. It even has features such as if I wanted to, let's say, edit this file called text.sh, I can click on this little icon here and say edit. It opens a text editor for me to edit. So I can start typing more text in here, and then I can tell it I want to save it. Close this out. And if I now were to view this file in the same way, there's a view, I'll see that my change, well, actually you can't see this one, but it will show that my changes are there in that file. So instead of having to learn a more complex command line based text editor, such as one called Nano, which we talked about last week, Emacs or Vim or VI, it has a nice simple editor for most people to do the simple edits of text files all in the web browser for you. It also allows you to sort of navigate through the file system. So if I wanted to see what's in, the examples directory, I can now navigate through that to see what files exist in those directories. Jobs, I typically skip over, but it has the abilities to sort of do job submissions with a templating system that we won't cover or really won't talk about today. Clusters basically allows you to have a shell or SSH session on a cluster. So we have one set up for Mana. So if you were to click on that, it'd open up basically in your web browser an SSH terminal. So this is where you basically are trying to SSH the machine. You have to do everything by command line, but you just have the same exact representation as we saw with the file browser and Open on Demand, just in a text form. And then finally, we have the interactive apps, which we have things such as desktop, which is basically a virtual desktop. So basically they'll create a desktop remotely on a compute node in the cluster for you if you have some type of graphical task you need to do. We have things like Jupyter Lab, if you're going to use that for your work, which we're going to use in this workshop. Jupyter Notebooks and our Studio Server as well. Let's see here. So did I cover everything? Chrome browser, interactive apps, yes. So if you were to click on, for instance, Jupyter Lab, you'll be presented with a form, which in the next section we'll go over and actually have you submit the job basically so that you can actually get working in the actual context of this workshop. So I guess before I hand it off, are there any questions about sort of what HPC, generally what HPC systems are, different ways to connect to it, and different tools that are surrounding HPC systems at this point? If not, I will hand it off to Didi for the next section.
Can everybody see my screen? All right. Thank you, David, for covering the introduction part. Now, this section of the tutorial, I am using deep learning as a use case to understand like how to use those HPC resources for your own research. But before diving into that, let's get the HPC resources and do some preliminary setup. So now, as David explained, like what Open on Demand is, what its features are, and how you can access those features. So continuing from there, we'll focus on one of the interactive apps available on Mana, which is called Jupyter Lab. It is a web-based interactive application which actually makes working with data science, machine learning, and scientific computation very easy. So let's create a notebook first by asking for resources for our work. So if you guys can just go to interactive apps and select Jupyter Lab. Sorry. So if you go to this section, this is the use case which will be following right now. So if you can enter workshop in the partition section. And number of hours, we'll just go with 3 hours. It depends on like how long you want to work, or like how long you'll be using those resources. Number of nodes is just, let's just leave it 1. Number of tasks is 1. Number of cores, let's select it 4. Now it depends on like if your application, or like if your work includes more of the parallel computing stuff, you can use number of cores depending on that. But right now, like for this, we've just used an arbitrary number. Number of RAM, if you can actually select 24 GB and 1 GPU, select any GPU type and just launch the system. Please let me know if you guys got through this. Okay. All right, I'll move on from here. Now let's connect to Jupyter Lab. Right. So what we have here is Jupyter Lab as our interactive environment. So why do we use Jupyter? Why do we need Jupyter? Now, first thing is like mainly since we're using Python for this tutorial, we'll be using Jupyter Lab. But if you prefer coding in R language, you have RStudio available on Mana as well. But why specifically Jupyter? Well, the main reason is like this is something which most data scientists prefer. And the reason for that is like it provides you an interactive platform to store your data, your code, your visualization plots, equations, markdown text, all together, all in one place. So it gives researchers the flexibility to actually analyze their work and streamline a workflow for their project. Another advantage is that it provides a collaborative space where you can easily share your files with your peers in multiple formats. And this is something important because when you are working in a collaboration, like when you're collaborating with someone, there are good chances where they have like different systems or like different versions of the packages you are working with. So it's good to have like, multiple formats to work with. Also, it becomes easy to edit the code in an interactive environment and like rerun the cells without affecting the other blocks of the code. And finally, another thing is like Jupyter is a language independent platform which supports like more than 40 programming languages. You can interact or you can work with whichever programming language you are comfortable with. But the next question comes is like, as you saw on our interactive apps, we have Jupyter Lab and Jupyter Notebook both. So what's the difference between Jupyter Lab and Jupyter Notebook? As I mentioned, Jupyter Lab is more of like an extension of a Jupyter Notebook. So a notebook just allows you to access one Python notebook in a virtual environment, but Jupyter Lab gives you an overall interface, like a better user interface. So here you can use the Python notebook files or the plain Python files, and you have access to the file browser system, which lets you upload, download files, rename it, everything. And you can work with multiple notebooks with Jupyter Lab, and also like in multiple environments, all in the same window. So how is it working? Okay, I'll get to that later, but just know like basically there are different code blocks or like cells where you write your code, and then it passes to the backend kernel, which actually runs your code and returns you the output. Okay. All right, now that we have discussed the Jupyter Lab and Jupyter Notebook and the interactive application, this is more about like writing our code. but how to access all these softwares and libraries which we are going to need for our work. So for that, we have package managers. So package managers are like software packages which are already installed on the cluster, using which you can install required libraries or softwares, and even you can choose, like you have the flexibility to choose specific version which you want to install. So if you can open the terminal, if you go to this, if you select this plus sign and like select the terminal from here, please feel free to interrupt me if I'm too fast, or like if there is any problem.
So you might want to share your screen with the actual Jupyter instance, Aditi, so we can see what you're clicking, like the plus symbol, things like that. If you can. No, we're seeing the slides right now, or the episode. Yeah.
Can you see now?
Yep, we're good.
Okay, sorry. If you select this plus symbol and go to the terminal section. Okay, all right. Now, if you just type module aware, it gives you a list of modules which are available on the cluster. If you can do something like module list, this will give you the modules which you have loaded, or like if you something which you have loaded for your specific application. One thing I want to clear, like I've been using the term environment a couple of times, and you may want to know like what exactly do I mean by that, and I'll show you what an environment is, and why do I need a Python environment. So when you are working on different projects, or like different applications, or you're working in collaboration with someone, there is a possibility, as I mentioned before, that the different peers, your peers may have different machines which might support different versions of a software. So it would be helpful if we can set up an isolated Python environment for that. An environment is just like a directory which is specific, or which is like isolated to a project, where you can install all these software dependencies which you want to use and their specific versions which you'll be needing. To create an environment, we have okay. So to create an environment, there are two most popular tools which people use. One is pip, and the another one is Anaconda. Pip just installs like Python. It is mainly for Python packages only. And Anaconda is a package manager, which is mainly used for like Python and R programming languages for scientific computing. The main difference between these two is like how they both manage the packages and software dependencies. Just a little note, like there was a problem with pip previously, where if you install a software package, it will do it in a recursive loop, because it automatically installs the dependent packages without even checking if if it already exists, or if there are currently different versions installed already. And because of that, it used to give a lot of errors. Whereas Anaconda analyzes your environment, check for all the pre-installed libraries, their versions, and install the compatible softwares accordingly. So let's discuss a little bit more about Anaconda, because this is what we'll be using for today's workshop, and why is it more preferred. So as one point I mentioned is like it gives fewer errors by analyzing the environment first and then installing the packages. Another important advantage is that it can install softwares which is written in any programming language and not just limited to Python. And Anaconda environments don't really interfere with each other. Like we want an isolated environment so that it does not interfere with other environment or like other application which you're working on. So with that being said, let's set up our environment for this tutorial. Okay, so in your terminal, if you can do module load Anaconda 3, you can find all the commands on the GitHub page. I'm sorry, I'm not able to share both the screens right now. Is everyone with me? Is it okay? Okay. Okay. All right. So we loaded our module. Now let's create an environment named as TF2. You can name it anything, but it depends on like whichever name you want to use. I already have one with this, so I'll just create a new one. When you create a new, when you load the Anaconda and you create a new environment, it will set all the environment variables for you, so you don't have to worry about anything. Now, if you go inside that environment, you can just do source activate and your environment name. So you are inside that environment specifically. All right, now that we have our environment, we want to install the relevant libraries which we'll be using today. So if you guys can just copy paste these commands and like install these libraries. Might take some time. Is it working for everyone? Just want to check in. Yes, it will only be installed in that specific environment. That's the thing we want. We don't want to, merge two environments which might have like different versions of a specific package or software. If you're done with this, like you can move on to the next one and install this. I'm sorry, it's taking a lot of time. All right, I'll install Matplotlib. Okay, as Sean mentioned, like you can just do it all in one line. I'm sorry, I didn't know about that. Did it work okay for you guys?
So how many of you have actually installed all the packages at this point? If you put a check mark or, thumbs up somewhere or chat, let us know.
Okay. Right, looks like almost everybody has it. Right, now, even though we created our environment, Jupyter still cannot access it because it cannot see like, it's more like it does not have an interface to access those the environment and all these libraries which you created. So we need to create a kernel through which it can actually use this. So let's create an Ipython kernel. And to actually make it visible, we have to create it and like display it in the directory. Did everyone do this? All right. Now, if you go here, you should be able to see your the kernel which you just created. For me, it's workshop. I already have a TF2, but it should be available. Just let me know if it worked for you guys and everything went well. So does everyone has a kernel named TF2? If it didn't show up, can you just refresh the page or like give it few moments for it to appear? Yeah, it takes time to show up. So, okay, so is everyone on the same page? Like everyone has their kernel and everything all set up? Okay, right. Now let's upload our files like the one which we downloaded from the setup page. So this is one advantage, like you can directly upload your file here. And open that notebook. And on the top right side, if you can select the kernel for this specific notebook, it should be TF2. Are we good till here? If everyone did that, I'll go ahead. All right, so finally we are ready to do some deep learning stuff. But before that, let's understand what we are going to do. So we will be working with C510 dataset. Now, this is a very common dataset which is used in machine learning and for computer vision research. It is a subset of 80 million tiny image dataset and consists of 60,000 images in total. The images are labeled with 10 different classes, as you can see here. So each classes have like 5,000 training images and 1,000 test images. And each row represents a color image of 32 by 32 pixels with 3 color channels, which is RGB. Now, whenever we create a machine learning algorithm, the basic workflow to follow is like data collection, data cleaning and pre-processing, defining a model, training the model, evaluating or testing the model, and then improving your model. Like this is more or less a basic workflow which we use. So let's start with that. Okay. As you guys see, like you already have the entire code section written here, so we'll just go with that. Now to run this, you can either use the run button or like just do shift enter. Is it working for everyone?
I'm sorry, I have the kernel uploaded as TF2, but can you go back just before you uploaded the downloaded notebook to your?
Yeah, so did you upload the notebook?
Yes, I think so.
If you just click on it, you should be able to open it.
Yeah, I just see it as a .text file. I'm not sure if that's uploaded correctly then.
Did you save it as the Ipython notebook?
Yes. 1 second. You can continue on though, sorry, I don't want to hold anybody up.
Okay. All right, so this is working for us. So this is like importing all the relevant libraries using which we'll be using those functions. Now the next section is like to check if you're using a GPU versus CPU. We'll get to know why do we need to have GPU. Okay. We'll get to see the difference between that, but this is how you can configure like if the TensorFlow is using GPU or not. So like this is a small challenge for you, but how would you check for a CPU? Like as I mentioned, this is how you are detecting a GPU device. So can you guys try and like, you know, check for the CPU device here? And let me know if it works for you or if you're able to do that.
I'm sorry, Aditi, can I interrupt real quick?
Please.
I was having an issue with the terminal. It installed everything, but I don't see the notebooks that we're on.
So like, were you able to upload the file? And if you click on that, it would just open for you. Were you able to do that?
Let me try again. No, it doesn't seem like it worked.
What's the problem exactly?
Well, first, wait, I'm sorry. The terminal window closed on me. There was some sort of error. It seemed like there was an error when I installed the, when I tried to do the step, the Conda install the Ipython kernel.
Can you like just?
I'll just try to run it again. It's okay. Let me see if I could run it again and see. Perhaps it was just an issue. I have to troubleshoot the error I got. Sorry, I didn't want to fall too far behind, but it's okay. It looks like it's collecting. It says collecting package metadata. It's doing it over again.
Okay.
I got.
Sure you're inside the environment.
Yeah, it was, but. Yeah, it says the current user does not have write permissions to the target environment.
Let me go look at your directory. I'll take a look on the back end. Sorry.
Okay. Thank you guys.
Though there's a question in chat, Aditi, about the thing I encountered yesterday when I tried this.
Sorry about that, guys. I don't mean to interrupt. It's just I was trying. You guys are getting far ahead, and I noticed mine just wouldn't work.
No, I mean, if you have problems, do speak up. You shouldn't just stay silent, I guess, during this presentation. So if you do have problems, you know, speak up or bring it up in chat, and we'll try and work through it on the spot, basically.
Or not being able to import the TensorFlow, can you just try and refresh the window again? Like sometimes it does weird things and you're able to get past that.
You can message me private if you want, David. If you guys want to go forward.
Yeah, make sure like on the top right side, you select the right kernel, which you have just created. Can I go ahead?
I'm okay. You could go ahead without me. I'll figure this out, and I'll just catch up to you guys.
Okay. So,
I don't know if anybody else needs help, but I'm fine. We'll figure it out. Thank you.
I think Luke might have a question as well. You want us to ask Luke your question to Aditi?
Yeah, sure, Aditi. So I have the kernel spec TF2 installed a couple minutes ago, and then I uploaded the notebook text, the download in the first episode, but it's just uploaded as a notebook.txt. So beyond that, I just don't remember what command you did. I'm looking through the episode we're currently on, but I couldn't find.
So did you save it as the? Let me go to the setup page, and did you click on it like as save link as and make
Yeah,
sure
that's correct.
it's an Ipython notebook file and not txt file?
Oh, hopefully. Okay. Yeah, that might be my issue. Okay, so I can just upload it as a IBYNB and then run it as that. Okay, let me check it out.
Sorry, where did you click on, Aditi? Can I see that again? What link you clicked on?
So if you go to home and the setup tab here,
Okay,
this is the notebook.
got it. Okay, and we'll just upload that.
Yeah.
Okay, thanks.
Okay, so if everybody is okay with that, now to check for the CPU, we just had to modify this and like mention this CPU. So if you put it here and like run it. Okay, so you should be able to see something like this, where it is telling you like you have two physical devices. One is named as GPU and the another one is CPU. Are we good with this? Okay. Right. So moving ahead, let's load the data set, the C510 data set, which we just discussed. And this is like the data shape. So these are the examples. This is the number of channels and like the pixel size and everything. So, and these are the number of classes which we'll be using later. Okay. Right. Now let's plot some examples from the data set we just downloaded and see how does it actually look like. So if we see, I plotted like 14 examples, and these are not very good looking images, but we can like somehow figure out that this is a frog, this is a truck, and deer, automobile, and something like that. Now, okay, now I'm creating an HDF5 data set. Now, why do I need an HDF5 format? This becomes important where if you're working with like a large heterogeneous file where it has different kind of or actually data in multiple formats, this becomes very useful because it has a fast parallel input-output processing. I'm not going to discuss it in detail, but if you want to learn more about it, you can use these links. But yeah, so this would create an HDF5 file for you. Does anyone have any problem? Okay. Thank you, sir, for posting that. All right, now moving ahead, let's define a model which we will be using to train our model with. Like this is a rather complicated thing, which is like specifically for machine learning people, but just to give you an idea, tf.keras. So keras is actually an interface which I mentioned it here, right? So keras is acts as an interface between the TensorFlow and Python, which works well with like the neural network models. And that is what we are using here. So we are creating a sequential layer. Now the convolution and max pooling layer and dense layer, these are all like very computer related specific stuff. So I'm not going to go into it right now, but if you want to discuss more about this, like you can ask me later. Right, now we are defining a data generator. What's the use of data generator? So like, we don't have to load the entire data set altogether, but it can generate data in batches. So like, let's say you have 100 examples and you select the batch size as 20. So it will give you, or like, sorry, batch size as 20. So it will give you 20 examples at a time to train your model. So there will be like 5 batches, and that actually, you know, like is a better thing rather than to upload the entire data set, and it consumes a lot of memory. So we define the data set. Now I'm using this HDF5 file. We have defined the batch size as 250, and I'm going to create batches for the training and validation set. And this is compiling the model. So compiling the model is more like the model which we defined here. So what when you compile a model, it actually builds that model layer by layer, and which can and then it goes for further processing basically. Now here comes like the interesting part. Let's start training our model using CPU, and it should look something like this. So is everybody with me? Okay. Okay, I have this working for 3 people. Okay. Epoch is actually a term used in machine learning, which defines like how many times, or like how many times the entire data set will be processed, or like it's more like the algorithm will run through the entire data set that many times, the number of epochs which you defined. So this might take some time. Please have some patience. Does anyone have any question at this point while your model is training? Liu, did it work for you?
Yeah.
Okay. And Jonathan, were you able to solve your problem?
Still working on it, trying to catch up here. Just
Okay.
a couple minutes, sorry.
Okay, so this is taking a lot of time, but let's just stop this and like, I mean, if you want, you can let it run, but we don't have that much time for our workshop. So I'm just gonna stop it. And now we want to compare and like see its performance and compare it with the GPU. So if you want to train your new, sorry. So this is how you create a new model. Like I'm just cloning the model because I don't want to mess up with the variables here. So I created a new model and I compiled it. Now we want to train the new model with GPU here. So can you guys just give it a try, like using this command line, like using this idea to train it using GPU, something which you did previously when identifying or CPU and GPU, and you can just give it a try. It's a very simple thing where you just have to specify GPU here. That's the only difference. So I'm gonna just copy paste this and try it here and like run it. So if you notice, it is comparably faster than the CPU operation. Should I? All right, so if you see with CPU, it was taking almost a minute, but GPU has like reduced the runtime by almost half. So like, or it improves or like it increased it, made it like 2 times faster. So that's why GPU is a better thing to use, specifically if you're working in deep learning or machine learning application. It comes in like very handy and very useful. Is this working for everybody with GPU? Are you guys still running with CPU or did you stop it and you're working with GPU? Okay. I'm going to make a small change here because since I interrupted the kernel in between, so here I mentioned I was trying to plot the history, which was a variable where the your model is saved, like the trained model is saved with CPU, but since we have interrupted the kernel, I would go ahead and edit this with new history, like the variable for GPU. So can you please like edit that meanwhile?
Sorry, I think there's been some, so we were trying to start a breakout room for some folks, and then I think there's been people, we're closing it now, but I think Aditi, I think it might have messed up your screen sharing. Sorry about that.
Oh, can you guys not see it?
Yeah, just reshare your DD from the DD account because it closed that one on accident.
Oh.
Sorry about that.
Okay, is it okay now?
Yep, we can see it.
Okay, so your model must have trained by now. Are we good? Like for everyone, did it run correctly? Did it train correctly? Okay, so now let's, just gotta make these changes. Should be good. Okay, so if you plot it, just so you know, like I edited the history with the new history, which is the variable for the GPU one. So this is how you can see how well your model did with like the loss and accuracy. We want our loss to be as low as possible and accuracy to be opposite. Right. Okay, so this is how our model performed, where it is giving me a loss of 0.8, which is still pretty high, but you need to like, you know, do some changes, like tune the hyperparameters and like train for maybe a longer time and like change few stuff, and it would give you a better result. And the test accuracy is 74%. Let's make some predictions and plot those predictions. So you should get something like this. Did everybody get a plot? Okay. So if you can see, like the Y is the actual one, the actual label which was there in the data, which was provided with the data, and P is the prediction. So it is doing pretty good, except for like a couple of examples where if you see it was actually an automobile, but it predicted a truck, and well, that's what a machine does. So it still did very good. I mean, it is still predicting a truck, and it actually is a truck. So this is how you can, you know, like observe how well your model did. And right now, apart from Mana, like there are other resources to do machine learning as well, which are like, you know, freely available to you. One of them is Google Lab, which uses the same interactive session as Jupyter Notebook. You can use it, but it runs on Google Cloud, like on the Google servers. So you can get like free limited resources, GPU, and you can upgrade your account to get a TPU as like a TPU as well. Another one is Microsoft Azure Notebook. There is Kaggle, there is Amazon SageMaker, and so many resources available out there. But just a small discussion question, and I'd like to listen, like hear your viewpoints on why would you need an HPC cluster over your own personal computer? What do you think? Like we need an high performance computing cluster when we have like our own system or PC and laptops.
I would assume that you would need an HPC in order to have access to like better GPUs. And maybe if you have a laptop, those, you know, a laptop might not have a great GPU on it for learning.
Yeah, well, that's somehow true. So like as David presented in one of his slides, where let's say if you're running 100 iterations for your project with like 100 different variations, do you think your computer has enough storage to do that, like to store it, or like do you think it is scalable? Because when you're working with deep learning stuff or like some applications on a large scale, it complexity and the size of the data set increases exponentially. And for that, you need like some, like some better resources. Also, these cluster actually saves money and resources where you don't need to have like big costly systems. Like not everybody needs to have that, but you can share those resources like in national labs and academic research, and you can have access to like more memory, higher speeds, faster processings and everything. So HPC is a good thing, and this is a very small demo to do machine learning, or like rather machine learning stuff on HPC and like use all those resources. But I'm sorry if there was any problem, but feel free to ask any more questions if you have. And yeah, that was all from my side. Thank you. Sarapong, you can continue your part now.
Yeah, can everybody hear me? Okay. Think, am I sharing screen right now? Can you guys see the screen?
No, not yet.
Oh, sorry. Okay. So I suppose, up until this point, was everybody able to get your Jupyter Notebook running from top to bottom? So this workshop is going to be sort of a continuation from the previous Jupyter Notebook. How do I see everybody's comment, by the way?
You pop the chat window, so there's probably a more next to your when you had share screen. So there.
So I guess no comments. Anybody needs additional help to get the Jupyter Notebook running or anything like that? Okay. Everybody seems good. Okay, so I suppose, for this part of my workshop, we're going to be discuss what is a file system, what is a distributed file system, and then we're also going to discuss optimization technique for increase our speed on distributed file system, especially on MANA. So we're going to be working with code that we worked with previously with Aditi's deep learning code. So yeah, so suppose the first question is, what is a file system, right? So some of you may have heard the terms from time to time. So at some point in time, you may have had to, format a USB flash drive or SD card or memory stick, and you may have had to choose between different options. So those are file systems, right? So you may have seen FAT32 or NTFS on a Windows. If you have a Mac, you may have seen, options between exFAT or Mac OS. So, sorry, I think I'm sharing your, move this away. So file systems are ways in which the screen seems to be flickering for some reason. Okay, sorry. Can you guys see my screen okay? So file systems are ways in which operating system organize data, right? So documents, movies, music, whatever on your storage devices. And why do we need file system, right? Because from the storage device hardware perspective, data is just sequence of bytes and binary bits and bytes, right? And those bytes themselves are not useful to regular users. So regular users like us, we mostly care about file and directory level abstraction. So we rarely work with blocks of bytes, unless you're really good at reading binary files, like David or something. Luckily, the file system under the hood handles the organization and locating logic of this block of bytes, and the user, can run commands like ls, and then they'll see a list of files. And really, also the file system. A good analogy also is if you can think of box of puzzle pieces, and the box itself is the hard drive, and the individual pieces are chunks of your data, right? Chunks of your document, like bits and pieces. And really what the file system is doing is that it's piecing together. So let's say I want to read a document, right? I'm telling this file system behind the scene is going to piece together these bits and bytes of data and pull everything together into one contiguous document. For example, in a Linux file system, file information is stored in an inode table. And essentially what, we're not going to talk about it here, but it's essentially sort of a lookup table that tells the operating system where to find blocks of bytes of data on the storage device, and so that when the user wants to read a file, they don't know how to stitch the file together into one complete file for us to read. So what is a distributed file system? So on a cluster, so like Mana, blocks of bytes that make up a single file, instead of being on a local hard disk, is now distributed across network attached storage devices, or NAS for short. And similar principles apply here. So the goal of the cluster file system is still to organize and locate blocks of data, but now it's across network and then present them to the end user as one contiguous file. And to answer Aditi's previous question, so the main benefit of having multiple storage devices clustered together in a network is so that we can increase storage capacity beyond what a single computer can have. Imagine, working with 100 terabytes of data on your laptop, right? I don't have that kind of money to buy a hard drive like that. Of course, the storage can be shared between cluster users, and now, and it further increases utilization of the storage devices. On Mana, there are two main distributed file systems that we currently support. So one of them is called Network File System, NFS, and Luster, that's another one. And Mana users have two special folders called Lust Scratch and NFS Scratch, where they can temporarily store data on the cluster. And I just want to point out that the Scratch folders will be purged after some point in time. So be sure to save all your data and don't leave it in the Scratch folders. So for our first coding challenge, let's locate the Lust and NFS file system Scratch folder on Mana. So if everybody can pull up your Jupyter notebook and then scroll all the way to the, sorry, where's that guy? Can you see my screen? So we all can go to the staging file system of choice section of the Jupyter notebook. Were you guys able to get to that? And then first, just run this cell cd. So this will point you to your home directory. And then for the first challenge 1, I just want everybody to execute these two commands in the Jupyter notebook cell and then run it. And then, so was everybody able to run your commands? Don't see any feedback. So, okay. Sorry, which page? The Jupyter notebook? The one on the right side? Okay, so if you scroll all the way down, so it's a continuation from the previous workshop. I'm sorry, previous section. It's just at the bottom of the page. You just gotta have to scroll down. Were you able to find at the bottom, like you gotta scroll down the Jupyter notebook, sorry, Jupyter Lab notebook, and then my section is at the bottom, I guess. Got it. Okay, so Okay, so first thing, please run the first cell. So it's essentially a Linux command cd, and it's just going to point you to the home directory within your Jupyter notebook. And then please execute the first challenge code. And we're just going to locate where the last scratch and NFS scratch folders. So I just want to point out that the exclamation point in front of the commands is sort of a magic symbol thing in Jupyter Lab that allows us to execute Linux commands. So in this case, we just executed pwd command, which tells us, where we are within the file system, the directory. And then ls is going to list all of the files within the current folder. And then as you can see, we have two scratch folders available to us, NFS scratch and LS scratch. And those are set up with two different file systems. So the NFS and the Luster scratch. So was everybody able to run the command? All right. Okay. So just a little bit about the two different file systems. So the first one is Luster file system. And really what it is that it's a parallel distributed file system where files operations are distributed across multiple file system servers. In a Luster, storage is divided. Sorry, let me increase this. Storage is divided among multiple servers, allowing for ease of scalability and fault tolerance. And usually on Mana, we want to work with Luster file system due to its high speed in read and write performance. The other file system is called Nfs File System, and it's a single server distributed file system where file operations are not parallel across servers, but a single server serves requests to the cluster. But the benefit is that NFS is an older technology and has the advantage of having gone through the test of time and is trusted among cluster architects. So how do you choose the right file system for performance, right? So depending on the user's needs, different file systems are optimized for different purposes. One may be optimized for random access speed, one with error correcting capability, or with high redundancy to prevent loss of data. But for this workshop, we will focus on disk random access speed on the Mana cluster. And as on the Mana, we have three locations for file storage, the home directory, the last scratch, as I was saying before, the NFS scratch folders. On Mana, our home user directory resides on an NFS file system server. So the deep learning code that we ran previously, we ran that from our home directory through the NFS file system. And though the home directory is great for storing our files on the cluster, it severely lacks in read and write performance. For the best performance, we will mostly want to use the Luster file system or the last scratch folder on Mana. And as discussed above, the reason is because Luster file system distributes workload across multiple meta servers, while NFS is a single server file system. And in addition to that, the Mana Luster file system is configured with solid state drives, while NFS file system is configured with spinning hard drives, which improves the Luster file system read-write speed even further. And you guys can read a little bit more about solid state versus hard drive performance here. And the gist is that, solid state is around 10 times faster can read up to 10 times faster and write up to 20 times faster than regular hard drives, spinning hard drive. So the next part of the coding challenge is we want to call this command usage. So challenge 2, and it's going to list our usage information of the storage. So you can see here that I have quota of 50 gigabytes for my home directory, 5 terabyte of raster scratch and NFS. And then it'll tell us, how much storage have you used so far on Mana. It's a good way to track, are we overriding the data, and then are we filling up the storage devices? So for the next part of the challenge, let us simulate write and read load onto the 2 different file systems so that we can see how they compare to each other. So for this challenge, we're just going to define 2 functions, write large file and read large file. And the parameters are path to the file that we're going to create. And within the write function, we're just going to write a number from 0 to 1,000,000, right? And then we're just going to write each character individually. And the f.flush is, we're going to tell the operating system to essentially write to disk immediately and don't buffer it on memory. And we're not going to get into that here. Yep, see you around. Was everybody able to define the 2 functions? So now for the next set of challenges, let's profile our code. So the first thing that we're going to do is we're going to write to our raster scratch directory. And then I also want to point out that there's another special magic in JupyterLab, %, 2% sign and time. So this is going to allow us to time the execution time of that cell, right? And this is really useful if you are performance conscious, especially dealing with deep learning. If you want to profile your code and see how quickly things are running, and then figure out where the bottlenecks are. Okay, so let's run this cell. And essentially what we're doing is we're going to write 1,000,000 characters, 1,000,000 numbers to the last scratch file system. And then we're going to do the same with the read operation. Wait a minute. It doesn't align with the title here. Sorry, we wrote, this is supposed to say write, and this is supposed to say read, but it's okay. So now we're going to read, and we can see that it takes around 1.6 seconds to write to the raster scratch file system, and around 80 milliseconds to read. And then let's do the same from our home directory, right? So the NFS file system. So we're going to write first. And then we're going to read. How's everybody doing? Are we all caught up? Profiling the code? Okay, so the write to our home directory is going to take some time. You can already see the difference in write speed, right? Like right now, we're just waiting. I think last time it took me around a minute. So nice. So let's just wait for this to finish. Okay. Sorry, I guess it took a little longer. So it took 2 minutes to write. So here you can see a huge difference, right? In terms of write speed, you may notice here that in this case, we don't see any improvement in read speed. And mostly the reason for that is because we are doing sequential reads. And also the fact that the created file is too small to show difference in improvement. If you're dealing with larger files, that's why you'll see a much more dramatic difference in read performance between the two file system. Okay, so now that we sort of understand what the two different file systems are, let us go back to Aditi's code, and then we're going to retrain our model. But instead of reading the file from our home directory, we're going to be reading it from the Lustre Scratch file system. And the first thing that we're going to do is we're going to download the file. We're going to save the training data file into the Lustre Scratch directory. And as you can see here, and just run this cell and let it running. And then from there, we're going to update our data generator. So to now point to the file within the Lustre Scratch directory. So we're going to create two new variables for the training data and the validation data. And we just also append _lust so that we can distinguish between what we worked with previously. So just run that. And then that shouldn't be too long. And then from here, we can retrain our model, but let's use the GPU version of the training code. So we can just run this. And we can leave this running. We just run it for 1 epoch, and then we can just end it here. And I also want to point out is that as we were seeing earlier, the read speed didn't show a huge difference in terms of read speed between the two file system. And so we're going to see similar effects here where we're not going to see a huge improvement. And that's mostly due to the fact that the data set that we are training on, it's quite small. We actually did a test on a larger data set, C510, and with that data set, you'll see a difference in terms of read speed. But so this is just to illustrate, how one may use the Scratch file system. So the Lustre Scratch folder. And that should be it for this part of the workshop. Does anybody have any questions, or are you guys stuck on anything? Okay, I'm just gonna stop this here. Interrupt the kernel. So, yep. So I think that concludes this part of the workshop. I don't know, David, do you want to wrap it up?
So, I mean, at this point, hopefully you're able to sort of see, why the file system is important, choices like that, and why selection of CPU and GPUs for machine learning are important also on HPC, and what an HPC is. At this point, are there any, final questions, thoughts, anything else that you would like to know before we just wrap up the workshop today? Hearing none, I guess, yep, so we're done with the workshop. I thank you all for attending, and I thank my two presenters, Sorpong and Didi, for doing a wonderful job. And I hope everyone can have a great weekend.